Okay, so now we're going to deal with the mean value theorem, MVT. The mean value theorem, to me, is very similar, similar concept as the intermediate value theorem. It's based on the function within the graph and its relationship with the graph. And so, of course, we need a graph, like I said. So here is our graph. And on this graph, just like the intermediate value theorem, there is a function that is continuous and, in fact, differentiable, which just means that you can take the derivative of the function. So let's create a function from the points a to b that is continuous. Okay, so any function. Here we go. There we go. Here is our function from a to b. It's very continuous. It doesn't. There are no breaks. It's differentiable. The derivative can be taken. And the mean value theorem states that on this continuous function, within this continuous function, there must be some point between a and b, which we'll call point C, where the instantaneous slope, or the derivative at that point, equals the average slope from points A to B. So the way to go about this is first and foremost to figure out the slope, the average slope from A to B. And if we do that, if we remember that average slope is the change in y over the change in x, rise over run. And that's really how we find it. It's quite simple. And the way to do this graphically is just to draw a line from one point to the other. And so I'll change colors to do this. Here is our average slope. Oh, let's not use that. Here is our average slope. Perfect. So this is the average slope throughout the entire function. And let's say that this slope is 1/2. M equals 1/2 from A to B. So this is very simple. Here's the next step. Now, when we look from A to B, we pick our point C, like I said earlier, and at that point, at any point C, the instantaneous velocity on the graph, on the original function, must equal the average slope of the entire function. So where on this graph does the instantaneous velocity equal the average slope? Around. And there are usually more than one places on the function where this happens. From my perspective right now, I can see one quite clearly, and that is right here. This will be our C point, or one of our C points. So right here, if we're to draw a tangent line, which I'm about to do, you'll see that the slope is parallel to the average slope. It's going to be quite close, so I'm going to draw it a little bit below, but I'm drawing a line tangent to that point right there. And that's just about as good as it's going to get. That is our instantaneous velocity at point C. And as you can see, it equals the average slope from A to B. And that is the mean value theorem. There must be a point C that has the same instantaneous velocity as the average slope. Now, in this next slide, I am going to discuss a real-world example. Okay, so here is our real-world example dealing with, wrong color, dealing with the mean value theorem. And we'll call it MVT. That looks like a J. Now it looks like a T. Okay, so this real world example has to do with cars and position and time. And so our situation starts off in a little suburban town, and a police officer sees, let's call him Alfred, sees Alfred leave his house in a hurry. So Alfred is on his way somewhere quickly, and he needs to get there quickly. And the officer, knowing this, loses track of Alfred, but sees him enter the interstate northbound. And in order to do this, or in order to track him and pull him over, this officer radios ahead to the officer patrolling at the next exit of the interstate that Alfred will eventually reach, because there's nowhere else that he can turn off. So this exit is exactly 15 miles away. So I'll draw a little diagram. Here is the entrance to the interstate, and here is the interstate. And let's say that this spans 15 miles. Now, here is the next exit. And at that exit, let's say, this is 15 miles. So at that exit, there is an officer in this little side area. And he is waiting for, she's right here. He's next to his car, and he's waiting for Alfred, who is on his way in his car. Okay. So Alfred is obviously in a hurry, and the officer knows this, and he communicates that with the next officer. And so Alfred, being from around the area, knows that there is usually an officer waiting at the next exit. So he cleverly decides that in order to reach his destination on time, he will drive very quickly just until before the exit. So he's going to drive very quickly up through here, and then right before he's about to get the exit, he's going to slow down, and he's going to go the speed limit. So the patrolling officer, let's call him Officer Tim, is smart, and this is Officer Tim right here. T for Tim. This is A for Alfred. And Tim is so he's smart, like I said, and as soon as the first policeman radios to him, Officer Tim starts his timer. So the timer is at 0, 0, 0 right here, and at this point right here, he will at this point right there, he will check the timer. And now, right as the timer reaches 10 minutes, so let's say Alfred is right here, and the timer reaches 10 minutes. Officer Tim sees Alfred cruising down the interstate at the required federal speed limit, because now Alfred has slowed down to the speed limit because he knows that Officer Tim is there, and he's right. So now Officer Tim turns on his siren, drives after Alfred, pulling him over. So they're at the side of the road up here. This is a patrol car, and that's Alfred's car, and this is the patrol car right behind. There's two cars next to each other. And so when Officer Tim approaches Alfred's car, Alfred immediately asks why he was pulled over, since he was doing the speed limit when he went by Officer Tim. And this is where Officer Tim utilizes the mean value theorem. Officer Tim says, "You boarded the interstate at the previous exit exactly 10 minutes ago." I know this, you know this. I was radioed ahead. And now, because this stretch that you covered is 15 miles long, you must have averaged exactly 90 miles per hour, because distance equals rate times time. So rate equals d over t, and the rate therefore equals 10 divided by time, which was 10 minutes, which is 1/6 of 60 minutes, or an hour. So 10 divided by 1/6 equals 10 times 6, which equals, oh, no, that was my bad. It's 15 miles. So 15 divided by 1/6, 15 times 6 equals 90. Let's see if I can make that a little clearer. So now he did the math. He now knows that, or it's been clarified that his average speed, Alfred's average speed, was exactly 90 miles per hour. So, so Officer Tim says, you must have averaged exactly 90 miles per hour, and when the speed limit is only 65. Even though you were driving at the speed limit when I saw you, the mean value theorem states that between points A and B, A being this point right here when he got on the interstate, to B when he passed Officer Tim, between those points, or the respective exits, the instantaneous slope at some point C in between, throughout this 15 miles, in between that stretch, some point C must equal the average slope, or in this case, speed, which is 90. Therefore, Alfred, says Officer Tim, I know that you went 90 miles per hour at least one point during your short trip. So here's your ticket. It would be superfluous to argue it in court. Now, I don't know if this is legal for Officer Tim to give Alfred a ticket, but it sure as heck makes sense, because it's impossible for him to have averaged 90 miles an hour and have followed the speed limit through the entire journey. So that is a real-world example of the mean value theorem, and in my opinion, it's interesting and, in this case, humorous. So thank you for listening, and I hope you enjoyed my real-world examples and my examples, or in my explanations, and I hope you learned something.